All right, good morning, everybody. Today, what we're going to do is we are going to learn about a new data structure called a BTree. Disappointed doesn't say as all things should be. So who said that? So Hector started out with a delightful pun. Just say disappointed. It doesn't say as all things should be. I should make my wife roll her eyes by telling that same joke later on. I'm not a dad yet, but I can practice the dad jokes now. Okay, so the whole idea behind BTrees is that they were studying the AVL tree, the group that developed this, and they're like, well, they have these really complex mechanisms, and with heaps, we can get the thing at the top, but what if I want to be able to store it in balanced form in a sorted order without having to have any of the worst case drawbacks of the binary search tree, but simultaneously without having to incur all of these penalties of the AVL tree. So those penalties are, we have this worst case scenario in the binary search tree that if we insert everything in sorted order, it becomes 10, 11, 12, 13, and so on. So basically it becomes a glorified singly linked list, but we also have these pointers that aren't really doing much of anything. And then what as we learned last week, that AVL trees have these expensive balancing mechanisms that while providing good find time and have some penalties when going with insertion and deletion. So the team that came up with the BTree, they were based out in Boeing. And what they were doing is they were trying to work on what are known as magnetic drum memories. And the drum memories were a bottleneck, and they were trying to store as much information as they possibly could into the drum memories. And to give you perspective, these drum memories could hold about 180 kilobytes. And this thing's about as big as the desk that I have here. And you need 10 of these to hold a modern cell phone photo. So we're trying to be very efficient with memory. And what had been dominating up to that point was hash tables. The drawback with hash tables is you can find things very quickly. However, they take up a lot of memory. And when you only have 180 kilobytes of information, that can be prohibitive. And as we've learned, AVL trees, they were just too complex to be able to implement effectively in these drum memories. So they needed to find a compromise. And so the idea behind a BTree was that we have more than one value per node, one or more values per node. And we're going to see the first half of it in lecture today. We're going to be discussing how we insert elements into a BTree. And the whole idea is that we propagate to the root and then we move up. All of the leaves are going to be at the same level. And the way that we grow a tree is we're going to split the nodes, and then the middle element is going to go up instead of trying to propagate down. So it's kind of the opposite thinking that we had when we were trying to implement a binary search tree. What we're going to learn on Friday is that after deletion, we will have a partial node. We delete an element, and this gives us an opportunity. We will merge these nodes together into a single node. And what this will allow us to do is ensure that the path to any root node, any leaf in the BTree is going to be the exact same. And so they go up on insert and down on deletion. So by the end of Wednesday's lecture, we'll have gone over several examples, and you'll have gone over several examples in the homework assignment of how to insert and delete from a BTree. Hey, does anybody have any questions before I continue? So here is an example of a BTree, and I want to go over the crucial concepts about how we would define a BTree. Every node has at most m children. So when we say at most, we have an example of at most here on the slide. I can never move this over, where I have 2 index records And then I have 3 child pointers. Does everybody see this? So you can have at most m children, which means we would have at most m child pointers. And that means we would have at most m minus 1 values in a given node. Now, every non-leaf node except the root has at least m divided by 2 child nodes. And so here's what I mean by this. Let me give you an example. Let's say I have 7, 10, and 12, and I have what we're going to call a maximum degree of 4. That means I have 1, 2, 3, 4 pointers. Does everybody see that? So let's say I want to insert 9, and this is at the leaf. So what I can do is I can say, well, 9 would normally go here. And so what's going to happen is I'm going to split this in half. And the way this will end up, and we're going to see lots of details about this, is 9 is going to become its own node, of which 7 would be its left child, and a node containing, I believe it was 10 and 12, is going to be the right child. So what we're going to do is we find a location, we find a value that will allow us to split and rise, and then we move it up as we insert. This also might help provide some clarity as to what some of these definitions actually mean. So when I say every non-leaf node has at least m divided by 2, in order to split it up, I had to fill the node first, right? And then I had to split it. So this was 3 divided by 2, and it has to have at least 1 here. Does everybody see that? So that's what's going on there. If it was 4, then I'd have 2 on the left and 2 on the right. The next part, the root has at least 2 children if it's not a leaf node. So that B tree that I just drew up again is a great example. In order to split it up, I have to raise an element and I have to have something to the left and to the right, which means I have to have at least 2 children in order for this to be a valid B tree. So we see here, this would be the root node, and it has at least 2 children. A non-leaf node with k children contains k minus 1 keys. So that means that if I have 1 value in the B tree node, So if I have 1 value in the B tree node, that means I have 2 child pointers. If I have 2 values in the B tree node, we're going to have 3 child pointers. Now, in the B tree definition, you will see the values inside the nodes commonly referred to as keys. But here you can think of values and keys as synonyms. They're just values inside. And as we mentioned earlier, all leaves in the tree must be at the same level. And so our splitting mechanisms will help us ensure that this rule is maintained. All right, does anybody have any questions before I continue? All right, so now I want to go through and walk through the definition, but I'm going to show you an example of a valid B tree. So here at the root node, we have keys of 22 and 30. The first, we're called left child. I'll put this in purple and large. So we're going to call child 0, has values 20 and 21. So we see that 20 and 21 are less than 22. Then child pointers 1 is values between 22 and 30. So 30 is the second key here. So we see that they have 25 and 28. Does everybody see how this traversal works? And on the right, where we call child pointers 2, we have 32, and I notate it as /0. But what we're going to see is that we're going to have a member inside a B tree node that keeps track of the current count. right, so let me take you through the animation. Every child has at most m children. So in this case, every child has at most 3 children. Then every non-leaf node has at least 3/2 child nodes. The root has at least 2 children if it's not a leaf node. And a non-leaf node with 3 children contains 2 keys. We see that how it has 2 keys in there. And as we can also see, that all the leaves are at the same level. Does anybody have any questions before I continue? All right, so what I want to do is I want to go through a couple examples of insertion with different maximum degrees. The way you'll see a question like this on the exam is I will say, given a max degree and a min degree, give me a binary tree, a BTree value. So in this case, the maximum degree is 3, which means the minimum degree is 1. And so at most 2 data values in each data structure. If it has a max degree of 3, it means it has maximum of 3 child pointers. That means just like in the diagram, it has at most 2. So at first, what I want to do is I want to insert 10. So first I'm going to create a non-null BTree node. And we'll see that the left child is 10. So the left key, excuse me. And then when I insert 7, what's going to happen is I'm going to move 10 over. So what's going on inside each BTree node is I have a sorting mechanism, which is actually going to move elements over. And if I find a location, all the elements to the right of it are going to be moved, and I'm going to put that element in there. Now, the drawback of using a BTree is you have to find a good balance between key size for a good balance. And if you make your keys too large, then you have too much sorting going on in each key. So we have to find a good balance there. So now what I'm going to do is I want to insert 11. So what do we think is going to happen here? Does anybody want to take a guess as to what we're going to do here with this BTree? Yes.
We're going to look at those 2 values there. It's like less than 7 will go to the left, and it's in between them, it'll go in the middle, and then it's greater than 10 will have it the right child node.
Okay, so here's what's going on here. So very good, that's exactly right. Since 11 is greater than all of the elements, and we've now exceeded the size of the node, we are now going to find the middle value and raise it up. So what's going to happen is we're now going to see that 10 is in the middle here, 7 is now on the left, and then the second child, so child pointer 0 and child pointer 1, so that's what I mean by second child. And we see how 10, 7, and 11 are now the new BTree. Does everybody see that? Yes. No, the max degree is this maximum number of child pointers that you could have in any given node. So in this case, the maximum, so for the question, for those of you in the chat, the question is, just to clarify what we mean by max degree. Maximum degree is the maximum number of child pointers. And so the number of values that can be inside of a BTree node is max degree minus 1. Okay, awesome. Any other questions? All right, so now can I get back to, okay, so sorry. So now what we want to do is we want to, so I want to insert 6, and 6 is going to move 7 over. And now what I'm going to do is I'm going to do 5. So what's going to happen is we see that 6 is going to be in the middle, and we're going to raise it up, and 5 and 7 are going to be left children. But now we've violated our property of the leaves, which is that all of them have to be on the same level. So here we have 6 and 10 is not full. So what I can do is I can say, well, 10 should move over here, and then I can make this pointer point here. Does everybody see that? And then I can do the same thing. I make this pointer point there, and this pointer point there, and 6 can be here. So let me go through the animation to show you what's going on. So first I would say, well, these must be at the same depth, propagate and combine up. So now we're going to combine these nodes. So what we're going to see here, 6 is less than 10, so I want to move 10 over. So 10 is going to get moved over, and we see that the first thing I do is I move that pointer. Does everybody see that? It's the same node at the same location, but instead of being child, so if I say that child pointer 0, 1, and 2, before 1 was pointing to it, so now I've moved it over to 2. And then you're going to see that I'm going to move 10 over as well. So at that moment, I have a duplicate. And now what I'm going to do is I'm going to say, well, that value where I want 6 to be, its right child should now point at the same location as the current pointer's right child. Does everybody see that? And then I want to move the left child to point to that same location as 6's left child. And guess what? I no longer need that node. And if I clean it up, we now see that all of the BTree leaves are at the same level. Right? So now here I'm inserting 13. And now I'm going to insert 12. So now we're going to do the same kind of process. And this is where on an exam, you want to keep track of all of these. So 12 is in the middle. So now I want to propagate 12 up, right? Now 6 and 10 is full, which means 12 is going to be moving up, and I want to propagate 10 up. Does everybody see that? So what's going to happen is 10 is going to be a new root node. Its first child pointer is going to be pointing to a new BTree node that contains the value 6. Its second child pointer, so it's 0 and then 1, is now going to be pointing at a new node containing 12, like so. And then if I want to insert 15, here's how I propagate. I go here, I've realized that I've got 12, the 15 is going to be bigger than 10, so now I follow this. I start here, 15 is going to be bigger than 12. I start here, it is empty, so therefore 15 can go there. All right, so does anybody have any questions? Yes. Right, so there's 2 different parts. So one, because I have different keys, I can maintain the number, how long it can be before I have to split. Right? The other thing is the balancing mechanisms are less complex. So as a result, it takes less time to execute. So if I'm putting in thousands or millions of elements into a BTree, it's going to run significantly faster than if I'm putting in elements into an AVL tree. So insertions and deletions in a BTree run much faster. And for those of you who want to move on to Dr. Wenninger's Advanced Databases elective course, you're going to go into a lot of detail about how BTrees are used in databases, because precisely this fact that they have a much faster insertion and deletion, and they're balanced. So you can use these keys to maintain key relationships. Did that address your question? Yeah. Awesome. All right, any other questions? Yes. They are all on the same level. So the question is, does this violate everything on the same level? So the keys, so the BTree nodes, all of these, this is at level 1, these are both at level 2, and these are both at level 3. Now the thing is that what I think the confusion might be coming in is that you're allowed to have more than one element per leaf node. But the tie break for 13 and 15, both of these have a depth of 3. Did that address your question? Okay, awesome. Any other questions? Let me check the chat as well. Do we have any other questions before I continue? All right, so now we're going to go to a max degree of 4. I'm going to work through another example. Oh, that gave away the game before I did anything. So a max degree of 4, what I was planning to ask is how many pointer child does a node pointer have? But the slide gives away that it's 4, right? And also gives away that the number of keys that I can have is 3. So what is for a max degree of 4, what's that minimum degree? So when I split, what's the minimum number of elements that I can have in a specific node? Yes. All right, so these are, I'm sorry, let me make sure I'm clear as to what I'm asking. We can have a maximum of 3 in a given node, but after I split, what is that minimum degree? So for example, if I have 7, 10, 12, and I insert 9, when I'm done with this, what's the minimum number when I split them up of values? Yes. So I have 2 in here, right? And then I would have 9 up here, and then 7 up here. So based on that, what is our minimum going to be? What is our minimum going to be? How many elements are in this key, in this node? 1, very good. So the reason we know this is because, oh, that's bad color for help for the eyes, 3/2, right? So we have to make sure that when we split this up, we can have 7, 9, 10, and 12 in a degree of 4. So if it becomes a max degree of 5, then what would happen is we'd have 7, 9, we'll say 11, and 12, right? So if I make this 8, I'll make this 10 to make it easy. So if I'm putting in 10, then 10 goes up there, and that means the min degree for that becomes 2. So the min degree is going to be the smaller. So if you have an odd case, it needs to split up, and you're going to have a smaller case and a larger case. Does everybody see that? So that's where we get this minimum degree. And if it's even, they're the same. So if I have, let me see if everybody gets this concept. So if I have a max degree of 7, what's my min degree? Because I have, I'm sorry, I have a max degree of 6. That's the largest number, of child pointers, right? So what's the largest number of values that I can have in this node? 5, very good, absolutely right. So the largest number is 5. And now if I fill it up and then I have to split it, what's the minimum number of elements that I have to have in a child after I split them up? I'm sorry, what? Just 1? So if we have, okay, I see where the confusion is. We need to split them in half. So what's going to happen is if I have a working machine, okay, so I have 7, 10, 12, 13, and 15, and I want to insert 11, right? So what's going to happen is it's going to split and it's going to raise one up and split them up. So this means that the minimum degree of the child here is 2. Okay. Does everybody see how that is? So if I have, let me just work through it one last time. Max degree of 8, how many child pointers do I have? 8, very good. That means how many values do I have? 7. So what is the minimum degree? 3, absolutely, all right, good job. Okay, so now let's work through this insertion and you all will see how this min degree and max degree and splitting will take things. So I have 10, 7, and 11. So what we're going to see is that 10 will be the initial first key. 7 is going to be before 10, so we're going to bump 10 over. And then 11 is after 10, so we just fill it in there. So far, so good, right? So now I'm going to insert 6. So can anybody tell me what they think is going to happen here? Let me move this up. Okay, so we have several comments in the chat that I've missed. I apologize. So it looks like everybody's kind of saying variants of correct answers. All right, so who wants to tell me what they think is going to happen if I try to insert 6 into this B tree? Yes. And I'll work together with the person saying it in the chat. So we have 7 is made the root. So is that what you, yep. Very good. All right, so we've combined together. So this will become 7. This will have 6, and then 10 and 11 will be on the right. So Jacob, that's what you're saying, right? Okay. I'll assume he's right. Okay, so yes. All right, very good. All right, so node plus 1 becomes even. So what we do is we divide by 2, subtract 1. So now 7 is going to become that root. And just like you all predicted, this is the new B tree. So now we're going to insert 5. And so what's going to happen is it's going to say, well, sorry about that. It's going to say that 5 is less than the first element. So we're going to go this way. And then here we're at a leaf. And 5 is less than 6. So we're going to see 5 and 6 here. All right, so next thing, I want to go through a couple other examples here. So we put in 9. What's going to happen is that 9 would be in the middle, so 9 would get raised up, 7 would become left, and 10 and 11 would become on the right. Now we have another scenario where I'm trying to insert 12, which would be the largest value, divide by 2 and subtract 1 since it's a number of values is odd. And so what's going to happen is 10 is going to become the new parent, of which 7 will be the left child, and 11 and 12 will be the right. Does everybody see that? All right, so now we're going back to our original problem. So we've inserted 5 correctly here. And now what we're going to do is we are going to insert 13. So 13 is larger than 7, larger than 10, larger than 11. And so 13 is going to end up here. So we see that this is one of the benefits, is that we can do a little bit of sorting mechanisms, but now we have a pretty good balance. As we start adding several, dozens, hundreds, thousands, and millions of elements into a B tree, these balancing mechanisms become much more beneficial. So now I want to put in 12. And so now we see that it's 10, 11, 12, and 13. So what I would do is I would have 11 split and rise like this. But now we also know that the next level up is not full. And so we need to do this in order to ensure that we can maintain the level integrity. So now what's going to happen is 11 is going to move. So 11 will be copied. And now where we have 11 in the new root, its left child is going to point to the old left child of 11. And its right child is going to point to the old right child of 11. So we see that the left child now points to the old 11 here, and then the right child points there. Does everybody see that? Then we can free that temporary node. And then if I'm going to click, I bet it's going to insert 15 on the next one, and it does, and now we have our balance. So some of the benefits of a B tree is if I'm trying to find, let's say I'm trying to find 6. I'd start here. I have to go through 2 elements. If I'm trying to find 10, it's 2. And if I'm trying to find 13, it's 1, 2, 3, and 4. So while there are some drawbacks, what we're going to see is that as more and more are inserted, that this becomes a beneficial approach. Okay, so quick interesting note, since Hector was making a joke about the B and B tree, there is no actual formal meaning of what B and B tree means. So there's several potential things. Rudolf Baer is one of the co-inventors of the B tree. So one people thought maybe it's Baer. They invented it while they were working at Boeing. So some people thought it might be bowing, balance is in balance tree, broad and bushy, like a big bushy beard, if anybody's ever seen hot clothes, right? There's all kinds of different things that it could be. And Rudolf Bayer, who invented it, co-invented it, he said that the more you think about what the B in BTree means, the more you understand the more you actually understand BTrees. So the co-inventor of the BTree is named Edward McCreight. I had the opportunity to have a conversation with him. I was kind of picking his brain on the best ways to teach this material. And he told us rather interesting story about when they were trying to come up with it. They were inspired by AVL trees. And so for a while, they were about to name it the BM tree. And for some of you in English, you might know precisely why it is you can't name it a BM tree. So they were like, that's kind of gross. Let's not call it a BM tree. And so they instead just went with the BTree. Okay, so badly named tree. So now let's start digging into the actual C++ implementation. So here, first I have a BTree node, and here's all the information we need in order to be able to construct the BTree node. First, I have the minimum degree. I have an array of keys, so template star num keys. Then I have BTree node pointers to pointers. So that's going to be an array of BTree node child pointers. I keep track of the number of keys itself. And then I keep track of a Boolean to indicate whether or not it's a leaf. So if it is a leaf, that's when we can split and raise. And if it's not a leaf, we have to consider whether or not to recombine and then split and raise. So we have these scenarios that we have to consider. And so here I have it labeled as well. We have the keys and then child pointers. If we remember that a pointer to pointer, just like in char star star, we have a pointer to a set of registers that contain pointers to arrays. So in this case, what we have is we have a pointer to a set of pointers, and all of these are pointing to other BTree nodes. That's why we say BTree node star star child pointers. Next thing I want to do is I want to show you the BTree node constructor. So we take in the degree, and when we construct it, we indicate whether or not we want it to be a leaf. So then from there, I can say that I have the minimum degree. The number of keys is going to be 2t minus 1. And then the number of child pointers is going to be 2 times t. I set the initial number of keys equal to 0. And then we set this equal to the leaf in. And so this is beneficial because if I'm at a non-leaf node and I have to recombine and split, I want that new node that we're going to create to also not be a leaf. So we're going to take advantage of that knowledge to help build the tree. So now I want to show you the code that we're going to use to actually split the binary tree node. So I have BTree node Y. And what I'm going to do is I'm going to create a right child. So here's the important thing. Because this is a member of the BTree node, I am reading in a node, but I also have a member of the node itself of child pointers. So what I'm doing is I'm reading certain keys into the right child, but what we're going to see later in this code is I'm going to set values into this node's own child pointers. And the reason I mention this in part is because I am not calling this by reference. So any of the changes that are made to this are not going to be reflected. So the first thing I want to do is that the node I'm reading in that I want to split, I create a BTree node pointer right child, and I pass its minimum degree and whether or not it's a leaf to its constructor. Then what I'm going to do is I'm going to say right child is equal to num keys is equal to t minus 1. And what this will do is then I can iterate through and get all the keys from this node that I want to split, and everything to the right of t minus 1 is now going to be in this right child. Everybody see that? So now I'm getting everything to the right of where I want to be, and where I want to be is a location I. And from there, what I want to do is I'm going to have everything to the left be another child. And now I want to copy the last children of t to right child if it's not a leaf. So now what I'm doing is I'm now not just copying the keys, I'm now copying the child pointers. And if it's not a leaf, now I'm doing that scenario where I'm getting all the values below and being able to update them. So this accounts for any size number of keys. Does that make sense? So now after I do that, what I'm doing is child pointers is a member of the calling node. Not Y, not right child. Now what I'm doing is I'm getting everything to the right, and now I'm moving it over in the child pointers. And what I'm doing is I'm using this to create space for where I'm going to put the new pointer that I'm going to rise up. Now, based on this, what's happening is I am going to set that particular child pointer equal to that child pointer that I created, that right child. And now from there, what's going to happen is I am going to iterate through. I'm going to start the other direction and go this way with j minus minus, and then put the rest of the keys and move them the other way. And then I'm going to copy the middle key, and then finally what I'm going to do is I'm going to increment the number of keys plus 1 to account for the new number of keys. So now what I want to do is this split child is called by a method called insert nonfull, and it's going to pass in a key, excuse me. And what I have is on the right, I have an example of a BTree node where it contains the values 2 and 20. And what I want to do is I want to insert into a nonfull node with the value 15. So here's the way this works. I'm going to set I is equal to num keys minus 1. So I have num keys is equal to 2. Therefore, I is going to be equal to 1. Right? 2 minus 1. And then if leaf is true, and in this case, we're going to assume that it is, while I is greater than 0 and keys I is greater than key. So in this case, 20 is greater than 15. So now what we're going to see is keys I plus 1 is equal to keys I. So this is kind of how we're actually going to perform that motion. What you're going to see is 20 is going to be copied over to the next key location. And momentarily, we're going to have 2 copies of 20 in the node. But then what's going to happen is we're going to have I minus minus. So we're going to see that now I is equal to 0. I is equal to 0. And then what's going to happen is if I is greater than or equal to 0 and keys of 0 is greater than key, well, 2 is not greater than 15. So we're not going to stay in the while loop. And so now that means we have found the location that we want to put the value 15. So keys of I plus 1, so that's 0 plus 1 is equal to key. So we're now going to see, you see it here, that 15 is now a member of the BTree node. And then from there, we're going to say num keys equals num keys plus 1. So now we have 3 keys in the BTree node. Does everybody see that? So next, if I want to insert into a nonfull, I have to consider the scenario in which it's not a leaf. And this is where knowing the is leaf is important. So if it's not an is leaf, we have to find where we're going to have the new key. And then we have a scenario where child pointers num key is equal to 2t minus 1. In that scenario, it means it's actually full. So from there, what's going to happen is we are going to actually split the child. We're going to pass that I plus 1 child pointer, and that's the child pointer we're going to split. And then what's going to return is going to be that new node that we're going to rearrange. And then after the split, what we're going to do is we're going to set keys of I plus 1. We're going to iterate through. And then when we get that new value of I, then we're going to call that insert non-full again. And what that's allowing us to do is it's allowing us to go back in and insert at the right location. So what we've done is we've rotated. So let's say the value that we are inserting is greater. So we have a value that we've split up and the value we want to insert is greater. What that's going to do by iterating that I is going to allow us the exact location we want to put in the insert non-full. So it's going to know that we want to insert that value there. Otherwise, if we're putting it to the left, it'll actually not increment and it will be over there on the left. All right, does anybody have any questions on this before I continue? All right, so for the BTree class itself, just like with a binary search tree, and just like with an AVL tree, and just, well, not like with a heap, because a heap we had an array, but in a BTree, we have a BTree node pointer called root. And that root pointer is the thing we can move around. And we can move that around because we can't move the location of this. So we move the root pointer around so we can tell which particular node we want to start at. And then we keep track of the minimum degree there. And I do the same thing. We read in the degree value, and then I set that root pointer equal to null initially, and then I set that degree equal to the degree in. All right, so for insert, and I would actually like to bring up the code to show you insert, so it'll be clearer. So here's where the insert method is. And the first thing I do is I say, well, if root is equal to null, then I'm just going to create a root pointer, a BTree node, and then I'm going to set the initial key, so that's keys of 0, equal to the key that I'm reading in, and then I set the number of keys equal to 1 for the root. So far, so good. Otherwise, we actually have some nodes in here, and now we have to consider what's going on. So if the root is full, so if root num keys is equal to 2t minus 1, that means we have the maximum number of keys that we can have in this particular tree. That means I have to create a new node pointer called S. S is for split. And so we're going to split this. So the root for the child pointer, or set S's child pointer is equal to root. So that's going to become, that left child is now going to become the old root. And then I'm going to split the root node. So what's going to happen is the value that's going to be propagated up is going to have its new value at that key of 0. And then the right child is going to be the second part of that split. So once I have them split, what's going to happen is I am going to make sure that the value I'm moving up is put into the right location. And that's where I start iterating through. And then by doing this, this allows me to do the insert on non-full. So what happens is I have it all set up, and there's a spot that's available where the value I want to insert should go. So what I call insert non-full will go straight to that particular node. So the benefit of BTrees is that after I perform the split, none of them are full anymore. And so therefore insert non-full will work. And so otherwise what happens is if it's not full, then it's easy. Then I just insert non-full, and that's easy to run. All right, does anybody have any questions before I run some sample code with this? Okay, the next thing I would like to show you is a in-order traversal. So in order traversal, what I'm going to do is I'm going to pass standard OStream out. I'm going to call by reference. And then if it's null, we're just going to say it's an empty tree. Otherwise, I'm going to recursively call a private method where I'm going to pass the root pointer, the output O stream, and the number 1. I'm going to tell you what this means. So I'm going to scroll up to the private method, and I have the current pointer, the O stream out, and I call that number level. And so what I'm doing with the in-order traversal is I'm not just printing out where it's going to be. It's going to print out the exact ordering of the B tree, but I'm going to pair it with the level that it's at. And what you're going to see is that there's not going to be a stray number that has, like if all of them are 3 except there's 1 at 4. What you're going to see is that the B tree is balanced. And the way that we do this is we start out and we know that, for example, if we have a max degree of 4, this means I have 4 pointers and 3 values. So those are the number of keys. So I would say 7, 12, and 14. And so what I do is I first print in order. So I traverse, then print, iterate, traverse, then print, then traverse, and then print. And so that takes me through all the number of keys. And then the last thing I do is this last print in order. That accounts for, well, that was not the right color. That accounts for this last pointer here. So in the event that I have large values larger than 14, that in-order traversal will catch it that way. Does that make sense? And so in the first one I want to show you is BTreeTest. And in BTreeTest, what I have is I've written a function called insert and print, where I call the B tree by reference, and then I pass these values, and then each time I print in order. And so what you can see on the output is not just the values in the tree, but where they're going, and you can see how the tree is changing at each level. So let me run make BTreeTest. And we see initially we have 15, 10, and 15, 4, 10, and 15. And so this is a min degree of 2. Sorry, yeah, we have a min degree of 1. Now here we have 2 here. This tree is 4, 8, 10, and 15. So we see the different levels, right? We see that split, and we see that it keeps splitting. And I'm actually able to get all the way here, and no value is lower than 2 in the particular tree. Hey, does everybody see that? You can see how all the splitting and how all the rearranging is working in order to maintain the balancing. Skip past that one. The other method I would like to show you that I've written, and this is how I'm going to conclude lecture, is I've written a method for traversal of the tree. And what this will allow you to do is once you have a constructed B tree, you can follow this approach to find the path to a specific value. So I have put in, I found several words in the dictionary were around structures, and no joke, in the dictionary, the third word after structures is struggle bus. So these are all the words, and I'm going to balance these out. They're put in alphabetical order. We were encountering one of the problems with a binary search tree. So then what I'm going to do is I'm going to print the traversal of the tree. And then what I'm going to do is find structure. I can pass structure there. And what's going to happen is you're going to see first the full tree, like so. And then finding structure. In order to get there, we have to pass structuralized and then structure. So what I want to do to conclude lecture is to show you, showing you that, showing you that, showing you that, showing you traverse. And so what's going to happen is I start at structuralized, right? And so it goes here, it finds it, and then structure is the next word. And so all of these are at the same level. I just did that to try to get them all onto the single screen. But if I actually put in struggle bus, we're actually going to see structuralized, structure, structureless, strudel, struggle, and then struggle bus. So if I modify this to say struggle bus, we now see that the exact set of words that I said would be there are printed out. And the reason we can claim this is because in traverse, what I can do is I just say, call the traverse, and then I would go through and traverse the tree. For print found nodes, which is the method that I call, I say seeking the key, and then I call print found nodes key. So this is calling the initial root node. So this is a private member of the BTree node. Insert not full, split, find key, traverse, print found nodes. So here what I'm doing is I'm iterating through, and actually, you know what? This would be a good place to start because it's 11:16, I'm over my time. So I will start here on print found nodes, and then what we're going to do on Wednesday's lecture is we are going to go into detail about BTree deletion. All right, so if no one has any other questions, you're free to go.